Okay, students, this is one numerical of spring. Okay, here the numerical is a safety valve 40 mm in diameter is to blow off at a pressure of 1.2 megapascal. It is held on its seat by means of helical compression spring with initial compression of 20 millimeter. The maximum lift of the valve is 12 millimeter. The spring index is 6. The spring is made of cold drawn steel and wire with ultimate tensile strength of 1400 Newton per millimeter square. The permissible shear stress can be taken as 50% of ultimate strength. Find wire diameter, mean coil diameter, number of active coils, and your modulus of rigidity is given as 81,370. Okay, so for this type of problem, let's understand the problem first. Okay, so here we have a valve. Okay, so normally take pressure cooker that whistle is a valve. Okay, so that this I mean I'll explain the example with the pressure cooker. Suppose here this whistle of the pressure cooker is the valve. Okay, and in that pressure cooker actually there is no spring, and it goes blows off due to excess pressure. Okay, but here let's say this one is actually held in its place. There is a valve like this. Okay, and some pressure is inside already, which is available. Okay, 1.2 megapascal pressure is available inside something. Okay, so and this is a safety valve. Okay, and this is being compressed. There's a spring like this. Okay, the spring is a compression spring, and it is already compressed to from initial length from I mean let's say the initial spring is length is this much. Okay, it is already compressed to 20 millimeter because of the pressure. Okay, so pressure is there, so spring is compressed due to the pressure, but it can further be compressed up to, you see, initial compression is 20 mm, but the maximum lift of the valve is 12 mm. That can be possible. That means it can still be compressed up to additional 12 mm. Okay, so initially 20 mm has been compressed due to the pressure. So we need to find out what is the force that is causing this deflection. Okay, so for 20 mm deflection, what is the force? Okay, and then you see, since the maximum lift of the valve is 12 mm. Okay, so that means what will cause next what okay, first of all, for 20 mm extension will like it as del 1. Okay, what is the force P1 that is causing this 20 mm? That force is due to the pressure here inside. Okay, due to the pressure there is a force on this valve, and that valve is pressing this spring to 20 mm. Now it can go to 12 mm additionally. That means initially 20 mm is there, next 12 mm will be added to 20 mm, so to get the final extension as 12 plus 20 plus 12 as 32 millimeter. So the force will be more than the initial force. Initially some force was there, that force has caused this to compress up to 20 mm. Now final compression is 32 mm, and the force will also be more. So what force is required to find, I mean maximum compression is 32 mm for this spring. Okay, right. So we have to design a spring, such a spring that it can withstand that the maximum value of its compression which it can take. Okay, so for what diameter of the spring, wire diameter, mean coil diameter, number of active coils, okay, we'll have this value of extension possible, and for what force causes this extension, that we need to find out. Okay, so from this relation, force is proportional to your extension. Okay, or extension or deflection. So if we write P1, then this is K into del 1, again P2 K into del 2. So if you take their ratio, P1 by P2 equal to del 1 by del 2. Okay, so from here P1 is actually, you have to find out first of all, if you are, so first pressure is given here, pressure is 1.2 megapascal, and the extension del 1 is given as 20. Now you know pressure equal to force by area. Okay, so you know the valve diameter is given to you. This is the valve diameter, that is 40 millimeter. In the question itself is given a safety valve 40 millimeter in diameter. Okay, so this is the valve diameter. So area, cross sectional area of the valve we can find out. So this pi by 4, 40 millimeter will convert to meter, so square. Okay, pi d square. Okay, pi by 4 d square. So this is the cross sectional area, and the force here is, let's say, P1, because this force is causing this force is actually has occurred due to pressure of 1.2 megapascal. So 1.2 megapascal is written in pascal 10^6. So if you calculate this, you get P1. Okay, that means a force P1 is exerted on the valve because of the pressure 1.2 megapascal. That is what we have found from this. Okay, so pressure 1.2 megapascal, area is this. So what is the force? This is the force P1 we have found. So actually in the problem also we have found the P1 here, that is 1507.96. we will get it as 1507.96 Newton. Okay, now this force is already present because some pressure is there, and it is, the spring has already gets compressed to 20 mm. So that is the initial compression and initial force. Now we have to design the spring such that it can take up to maximum possible compression. Now already 20 has been compressed, plus additional 12 is possible. So 20 plus 12 is 32 mm. That is the maximum possible extension. Now to compress, this is not extension, sorry, extension would be in case of tensile spring. For compression, this will be, we can call it as deflection. Okay, or compression. Now 20 initially was the compression, now this much 20, now we can further compress it to additional 12, so total 32. So for that, force has to be more than this one. Okay, because more force means more compression, right? So this P2 has to be found out. Okay, what P2 can cause the compression of 32 millimeter, that you have to find out. So now you see, from this relation P1 by P2 is del 1 by del 2. So from here P1 is 1507.96, P2 is unknown, del 1 is 20, del 2 is 32. From here you calculate P2. So you get here this one, this is actually written, you can read it. So del 2 here, P2 is 2412.74 Newton. Okay, and this is the force which actually can be applied to this spring. Okay, maximum force that can be applied to this spring, and maximum compression possible is 32 millimeter. Now what diameter of the spring coil? This is the spring, what is the spring coil diameter? Okay, this one, mean coil diameter is this one, and how many number of active coils will be required so that this force can be withstood by that spring, and this your extension also can be possible there. Okay, so that is what you have to find out. Now from the notes, you know, this actually was given to you, just a moment. So using these spring wire diameter, from this relation, shear stress equal to something called wall factor. Okay, this is wall factor, K multiplied by 8 PD divided by pi d cube. P is the force, okay, that is being applied, compression force that is being applied on the your spring. Capital D is mean coil diameter, small d is wire diameter. Both are unknown right now. So there is a relation. This C, capital C, is called spring index, and which is capital D by small d, and spring index is actually given in the question. Okay, so in this case spring index is 6. You see, spring index is 6. So spring index is given as 6. So C is given. Okay, now what do you need for this relation? You need the shear stress. So shear stress is 50% of ultimate stress, which is given in the question. The permissible shear stress can be taken as 50% of ultimate strength. So ultimate strength is 1400 Newton per millimeter square. Okay, ultimate tensile strength is 1400. So 0.5 multiplied by 1400 is 700, so put it here 700. K you have found, actually we have found at the beginning itself from this relation, from the relation given for wall factor. So this is the wall factor. K, you put C is 6 here, 6 here, so you get K. So K is 1.2525. After putting 6 here in place of C, we get 1.2525. okay, so that is 1.2525 multiplied by 8. This P that has caused the maximum, I mean we are designing for to design a spring that can take this load, right? So we have to take that load, maximum amount of load, and just we have taken one small d, I mean as a denominator to make the ratio of d by d, so that we can write C here, and this was initially d cube, now it will become d square. Okay, simple. Now d, only d is unknown, C is 6, so we can put 6 there. So d is unknown, so from here we can calculate small d. Small d is 8.12 we get, and we can approximate it to 9. So 9 mm is the diameter, I mean that is the wire diameter for this your valve. Okay, sorry, for a spring. So 9 mm small diameter, this is the spring, actually this is the spring diameter, this is the spring diameter. Okay, and mean coil diameter will be this one. Okay, so we have to next find out mean coil diameter of this spring. Now from this relation again, mean coil diameter, capital D is C into D. So C is 6, D is your 9, so 6 into 9 is 54. 6 into 9 is 54. Okay, so finally number of active coils. So from this relation again, number of active coils, we can find it, the number of active coils N, that is capital N, can be found from this relation. Okay, so spring diffraction relation, delta is equal to 8p d cube N divided by z into d to the power 4. So p is known, delta, if you take delta as 32, then p will be the final extension. If you take that, p will be the final force. If you take the initial extension, then initial force. I mean both will give you the same answer. So we have taken the final force and final extension 32, final force 8. So this is d, here is 54, we have got N is unknown, z is given in the question as 81,370. okay, and this d we have just found as 9. So from here we have calculated N as 5.42, approximated as 6 coils. So this is a numerical of spring, where we have to find out your mean coil diameter, wire diameter, and number of active coils. Similar numerical is given, another one. Let's understand. It is required to design a helical compression spring subjected to maximum force of 1250 Newton. The deflection of the spring corresponding to the maximum force should be approximately 30 millimeter. Okay, the spring index can be taken as 6. Okay, the spring is made of patented and cold drawn steel wire. Okay, the ultimate tensile strength and modulus of rigidity is 1090 and 81,370. The permissible stress tau is can be taken as 50% of ultimate tensile strength. So 50% of 1090 is tau. Okay, and they again design the spring and calculate wire diameter, mean coil diameter, number of active coils. So here it is actually simpler, this numerical is simpler. Here you see directly force is given as 1250. okay, you can read it here, 1250 is the force. Okay, compression force. What do we need? So for this problem actually we need K, P, and d by d. D by d is 6 again. Okay, d by d, the spring index can be taken as 6. So at the beginning we have just taken the tau. Tau is 0.5 times that 50% of SUT. So 50% means 0.5 times SUT as per the question. So 50.5 into 1090 is 545. Okay, so K is now from this relation of wall factor. So wall factor K has been found by putting C value. C is 6, so we have got K as 1.2525. So wire diameter from this relation. So tau is known, d by d we have just taken out, so that it there remains d square. So P is 1250, C is 6, and K is 1.255, and this is tau is 545. So D from here 4.37 or 5 mm. Similarly, mean coil diameter D is equal to C into D, which is 6 into 5 equal to 30 mm. Okay, from this relation. And finally, number of active coils can be found by using following this relation. They are equal to 8 into P into D cube and divided by G to the 4. So G is given, P is given, D is just found. We have D we have found as 30. So D we have found as 5, and N has to be found. Now delta whether it is given, you see, read the question. So the deflection of the spring corresponding to maximum force should be 30 mm. So maximum force is 1250. So for 1250 Newton force, the deflection delta is 30. So here this delta is given as 30. So we have taken 30 and this is the maximum force, that is 1250. Okay, so calculating this, we will get the number of active coils as 5.65 or almost equal to 6 coils. Okay. So these are some illustrative numericals which are simple spring design, helical compression spring design numericals. Okay, so thank you very much.